Let us now derive the torsion equation. So basically this is done in two steps. In the first step, it's to relate theta and the shear stress. So this is the shaft which is under the torsional, which is under torsion T. So because of this torsion, the point B moves to B dash, as we already discussed in the previous video, and therefore the point joining the center and B would look like this now, and the point joining A and B would look like this, and we've already discussed that this angle is nothing but shear strain gamma. This angle is theta. So observing this diagram, we understand that the arc length B dash could be got by two ways. One is considering it as an arc formed by the radius with an angle of twist theta. So PB dash could be written as R into theta, assuming that these angles gamma and theta are very small. And also the angle gamma can be taken into consideration, and let us imagine that this length from ear to ear is L, which is the effective length of the shaft. So this BB dash in terms of L and gamma should be L and gamma, where theta and gamma are both in radians. So we can equate these two. L gamma is equal to R theta. So we can write gamma as R theta by L. So this is the value of gamma in terms of R theta and L. And also we know that from Hooke's law, of course following the Hooke's law, modulus of rigidity G is the ratio of shear stress to shear strain, and shear strain could be written as gamma is equal to shear stress by G. So comparing these two equations, you can call these two equations as 1 and 2. Comparing this 1 and 2, I will substitute each of this. So R theta by L is equal to shear stress by G. To get this equation in a familiar form, we can rewrite this equation as tau by R is equal to G theta by L. So this is the relation between the angle of twist theta and the shear stress tau in terms of the radius of the shaft and the length of the shaft L. Now let us relate the torque T and the shear stress tau. So we know from the previous relation that tau by R is equal to G theta by L. So G is a material property which is constant. Theta is the angle of twist for a body which is under definite torque, and L becomes the geometrical parameter of the shaft. So if J theta by L is a constant, then we can write this tau by R is a constant. So which means that these two have a linear relationship. So let us now see the relationship between the shear stress and the radius. Let us assume that at a distance x from the center, the shear stress at this distance x is tau x, and at a distance at R, the shear stress is tau R. Okay, it's okay, you can simply name it as tau, because previously we have said the shear stress at the radius R is equal to tau, so we'll name just it as tau itself. So we have that by ratios and proportions, you can say that at a distance of x, it is tau x. So it is tau x divided by x is equal to tau by R, because these two are proportional. Then let us find, to relate this T and the shear stress tau, we need to find out the elemental area here, which is at a distance of x from the center. And if this elemental area is actually, if it is actually spread out as a segment like this, which looks like a rectangle, its length will be equal to 2 pi r, because the circumference is 2 pi r. So here instead of r, this radius is x, so I should call this as 2 pi x, and the thickness of this segment is dx. So the area of this elemental area is 2 pi x into dx. Also we know that shear stress is nothing but shear force, that is F tau, force for shear, divided by the shear area. Now we can say that the shear force F is equal to shear stress multiplied by shear area. And here, if you want the shear force at a distance which is at x, then we should have the shear stress at this point multiplied by the area along this segment, because it is at a distance x. So for that, I should write this as shear force tau, which is at a distance x, is equal to, and the shear stress at a distance x multiplied by the area of the element, which is at a distance x. So we already know the area of the element at x distance, so we can write this as 2 pi x into dx, which is the area, multiplied by the shear stress tau x. Now we know that the torque is nothing but the force into distance. So with this equation, we can say that the torque, which is at a distance x from the center, is equal to the force at a distance, the shear force at the distance x multiplied by the x distance. So we can write this as F tau x, which was previously written as tau x into 2 pi x into dx into x. So this becomes 2 pi x square tau x dx. From the previous relation, we have shown that tau x by x is equal to tau by r. With this idea, we can say tau x is equal to tau by r into x. Then this could be substituted here, and we have 2 pi x cube multiplying this x with x square, and then tau by r into dx. This is the torque on the element which is at a distance x, which is given by 2 pi x cube into tau by r into dx. Now to find the torque on the whole section, we need to integrate the torque along all the segmental sections from the center, which is at a distance 0 from x, 0 from the center, to the distance to r, which is to the periphery of the rod. So if you want the whole torque, we need to integrate this equation within the limits 0 to r to get the torque throughout the bar. So integrating this 2 pi x cube dx, and tau by r is a constant along with the 2 pi. So taking the constants out of the integration sign, 2 pi by tau by r, integral of 0 to r, which is x to the power of 3 dx. So the integration of this is 2 pi tau by r. So integration of x cube is x to the power of 4 divided by 4 within the limits 0 to r. So which is finally 2 pi by tau by r. So the upper limit is r to the power of 4 divided by 4, and the lower limit is 0, so it becomes 0. So the equation becomes 2 pi tau r to the power of 3. Here we need to be careful. We need to retain this r as it is without taking. So we'll write this as r to the power of 4 divided by 4, which could be written as pi r to the power of 4 and this divided by 2 and this tau by r separately. This term pi r to the power of 4 divided by 2 is called as the polar moment of inertia, which is specific to the circular shafts, and we can write this equation as T is equal to Jp, which is the polar moment of inertia, multiplied by tau by r. Of course, I said pi r to the power of 4. If you convert this as r is actually 2 d by 2. So if you take this d by 2 to the power of d by 2 to the power of 4 divided by 2 again, you get it as pi d to the power of 4. You can write it as pi d to the power of 4 divided by 32, which is which we already discussed, which is the Jp of circular shafts. So we already now related, we have now come to a point where we are trying to relate this shear stress tau in terms of T, R and Jp. So this shear stress tau was already related in terms of shear stress by R is equal to G theta by L. So we can take this tau by r this side and then we can equate the other terms here. So we can now equate these terms because this is equal to this and again this is equal to this. So we can write the final equation as T by Jp is equal to tau by r is equal to G theta by L. This equation is called as the torsion equation. So which means that to produce a unit angle of twist, you need more torque, and you will need more and more torque if the value of G is higher, and you will need less and less torque if the length of the shaft is longer, and you will need less torque if the radius, that is the diameter of the shaft, is larger, and you will need this is not related to R, only the terms related to G theta and L. So longer the shaft, you can expect more angle of twist. So this is the torsion equation, which is a very common question asked related to the torsion, because it is the only theory part which is generally asked in every examination.